CS stage with the diode connected load. In many CMOS technologies, it is difficult to fabricate resistors with tightly controlled values or a reasonable physical size. Consequently, it is desirable to replace RD in figure A with a MOS transistor. A MOSFET can operate as a small signal resistor if its gate and drain are shortened. Figure A, called a diode connected device in analogy with its bipolar counterpart. Here you can see the figure A diode connected NMOS and PMOS devices. B, small signal equivalent circuit. This configuration exhibits a small signal behavior similar to a two-terminal resistor. Note that the transistor is always in saturation because the drain and the gate have the same potential. Using the small signal equivalent shown in figure B to obtain the impedance of the device, we write V1 equal to Vx and Ix equal to Vx by R0 plus GmVx, that is the impedance of the diode is simply equal to 1 by Gm parallel to R0, similar to 1 by Gm. If the body effects exists, we can use the circuit in figure to write V1 is equals to minus Vx, Vbs is equals to minus Vx, and here you can see the figure A arrangement of measuring the equivalent resistance of a diode connected MOSFET. B, small signal equivalent circuit. Gm plus Gmb Vx plus R0 equal to Ix. It follows that Vx by Is equal to 1 by Gm plus Gmb plus R0 power minus 1 equal to 1 by Gm plus Gmb parallel to R0 is similar to 1 by Gm plus Gmb. Interestingly, the impedance seen at the source of M1 is lower when body effect is included. Intuitive explanation of this effect is left as an exercise for the reader. Now we now study a common source stage with a diode connected load for negligible channel length modulation. Equation can be substituted in equation for the load impedance. Here you can see the figure CS stage with diode connected load, CS stage with diode connected load, yielding AV equal to minus GM1 1 by GM2 plus GMB2 is equals to minus GM1 by GM2 1 into 1 by 1 plus N 1 plus neta, where eta is equals to GMB2 by GM2, expressing GM1 and GM2 in terms of device dimensions and bias currents. We have AV equal to minus root over 2 nu n C naught x W by L1 ID1 by root over 2 nu n C naught x W by L2 ID2 into 1 by 1 plus neta. Since ID1 is equals to ID2, AV is equal to minus root over W by L1 by W by L2 into 1 by 1 plus neta. This equation reveals an interesting property. If the variation of neta with the output voltage is neglected, the gain is independent of the bias currents and voltages. So as long as M1 stays in saturation, in other words, input and output signals vary, the gain remains relatively constant, indicating that the input-output characteristics is relatively linear. The linear behavior of the circuit can also be confirmed by large signal analysis, neglecting channel length modulation for simplicity. We have in figure 1 by 2 nu n C naught x W by L1 into V in minus VTH 1 whole square is equal to 1 by 2 nu n C naught x into W by L 2 VDD into VDD minus V out minus VTH 2 whole square, and hence root over W by L1 Vn V in minus VTH1 is equal to root over W by L2 VDD minus V out by VTH2. Thus, if the variation of VTH2 with V out is small, the circuit exhibits a linear input-output characteristic. The small signal gain can also be computed by differentiating both sides with respect to Vin. Root over W by L1 is equal to root over W by L2 into minus tau V out by minus dou V out by dou Vin minus dou VTH2 by dou V in, which upon application of the chain rule dou VTH2 by dou V in is equals to dou VTH2 by dou V out. Dou into dou V out by dou V in is equals to neta dou V out by dou V in reduces to dou V out by dou V in equal to minus root over W by L1 by W by L2 into 1 by 1 plus neta. It is instructed to study the overall large signal characteristics of the circuit as well, but let us first consider the circuit shown in figure A. What is the final value of V out if I drops to 0? If I drops to 0 as I1 increases, if I1 drops to 0 as I1 decreases, so does the override of M2. Thus, for small I1, VGS2 similar to VTH2 and V out similar to VDD minus VTH2. In reality, the subthreshold conduction in M2 eventually brings V out to VDD if ID approaches 0, but at very low current levels, the finite capacitance at the output node slows down the change from VDD minus VTH2 to VDD. This is illustrated in the time domain waveforms of figure B. For these reasons, the circuits have frequent switching activity. We assume V out remains around VDD minus VTH2 and I1 falls to small values. Now we return the circuit of figure plotted in figure versus Vn. The output voltage equals VDD minus VTH2 if Vn less than VTH1 for Vn greater than VTH1 equation holds, and V out follows an approximately straight line as Vn exceeds V out plus VTH1 beyond point A. M1 enters the triode region and the characteristic becomes nonlinear. The diode-connected load of figure can be implemented with a PMOS device as well. As shown in figure, the circuit is free from OD effect, providing small signal voltage gain equal to AV equal to minus root over nu n W by L1 by nu P W by L2, where channel length modulation is neglected. Here you can see the figure A, diode connected device with stepped bias current. B, variation of source voltage versus time. Figure input output characteristic of CS stage with diode connected load. CS stage with diode connected PMOS device. Equations indicate the gain of a common source stage with diode connected load is relatively weak function of the device dimensions. For example, to achieve a gain of 10 nu n W by L1 by nu P W by L2 W by L2 is equal to 100, implying that nu n is similar to 2 nu P. We must have W by L1 similar to 50 W by L2. In a sense, a high gain requires strong input device and a weak load device in addition to disproportionately wide or long transistors, and hence a large input or load capacitance. A high gain translates to another important limitation, reduction in allowable voltage swings. Specifically, since in figure ID1 is equals to mod ID2 nu n W by L1 into VGS1 minus VTH1 whole square, similar to nu P W by L2 into the VGS2 minus VTH1 whole square, revealing that mod VGS2 minus VTH2 by VGS1 minus VTH1 similar to AV. In the above example, the override voltage of M2 must be 10 times that of M1. For example, with VGS1 minus VTH1 is equal to 200 millivolts and mod VTH2 is equal to 0.7 volts. We have mod VGS2 is equal to 2.7 volts. The analog design of octagon. Note that with diode connected loads, the swing is constrained by both the required overdrive voltage and the threshold voltage. That is, even with a small overdrive, the output level cannot exceed VDD minus mod VTH. An interesting paradox arises if we write Gm equal to nu C naught x W by L mod VGS minus VTH. The voltage gain of circuit is then given by AV equal to Gm1 by Gm2. Gm1 by Gm2 is equal to nu and C naught x the W by L1 into VGS1 minus VTH1 by nu P C naught x W by L2 mod VGS2 minus VTH2. Equation implies that AV is inversely proportional to mod VGS2 minus VTH1. It is left for the reader to resolve the seemingly opposite trends suggested by equation. We should also mention that in today's CMOS technology, channel length modulation is quite significant, and importantly, the behavior of transistors notably departs from the square law. Thus, the gain of the stage in figure must be expressed as AV equal to minus GM1 into 1 by GM2 parallel R01 parallel R02. Where GM1 and GM2 must be obtained as described in chapter. Thank you.